This is part 2 of a two-part series on the mean value theorem, in which we talk about applications of the mean value theorem, something more substantial than catching speeding drivers. We do things like check the conditions for a function to be constant, to be increasing, to be decreasing. If you haven't seen the first part, go back and look at that video. Otherwise, just quickly review the statement of the mean value theorem, which is behind me.
So let's first look at how you use derivatives to check for a function being constant. You know on the one hand that a constant function has derivative 0. For example, if you take constant value 5 for a function, the derivative of 5 is 0. The derivative of a constant is 0. What about the other way around? If the derivative is 0, does that mean that the function has to be constant? Well, that's almost true, but here's the kind of thing you have to be careful of. This function has value 2 for x negative. It has value 3 for x positive, and I'm showing you the graph. It's not a constant function. Its domain is all the non-zero x values. And at every point where the function is defined, the derivative is 0, and yet the function is not a constant. Well, okay, so that's kind of a cheat, and I agree. And this is really the only kind of exception that can happen. If the function is defined on an interval, you don't have this kind of behavior. So what's special about intervals is they're connected. You can get from any point to any other point inside the domain. So domains which are not connected, you can't make any conclusion like this. So if your function is defined on an interval and the derivative is 0, then the function does have to be constant on that domain, on the interval. And I'm just going to talk about an open interval here because it's problematic to talk about derivatives at endpoints. So I know I said that we weren't going to do proofs in this course, but this is just such a short proof, and it gives you insight into how you use derivatives. So I'm going to give you the argument, and it's just a really short one. I have a function whose derivative is 0. I want to conclude the function is constant. How can I make that conclusion? So suppose the function were not constant. If the function is not constant, then it has different values at 2 points of the domain, A and B. Now, one of the 2 points is less than the other, so let me just suppose that A is less than B. It doesn't really matter. It's the other way around, same argument. So if f of A is different from f of B, then it means that on the interval AB, the average rate of change is not 0. And so according to the mean value theorem, there's a point C between A and B where f prime is not 0 because it's the same as the average rate of change. Well, wait a minute. No, that can't happen. We said f prime is 0. So this cannot happen. So it definitely cannot happen for a function whose derivative is 0 that it would have different values at 2 points. Can't happen. So that means that the function has to have the same value at every point of the interval. Now, this is not a particularly deep conclusion, but it's a surprisingly useful one. You want to check if something is a constant, if it doesn't change. Just check if the derivative is 0. It's a surprisingly useful technique. It gets used a lot. Can 2 functions have the same derivative? Can f and g have the same derivative? Well, if f is g plus a constant, then yes, they will have the same derivative. In other words, if f minus g is constant, they'll have the same derivative. And what we're saying is that that's essentially the only way that 2 functions can have the same derivative, is if they differ by a constant. Well, as before, it's only if the function is defined on an open interval, and otherwise, yeah, you're going to have some exceptions. So let's suppose that f and g are defined on the open interval AB, and they have the same derivative. Well, then look at the derivative of f minus g. So that's f prime minus g prime. And according to what we're saying, that should be 0. So the derivative of f minus g is 0. How can the derivative be 0? Well, it means that f minus g is constant. In other words, f is g plus a constant. Again, a very, very short argument, and as proofs go, this hardly counts as a proof. It's just making use of the mean value theorem, and it's, again, a surprisingly useful way to check how many functions can have the same derivative. So here is a good example of what we're talking about. Take f of x to be natural log of 7x. G of x is just natural log of x. These are both defined for x greater than 0. By the way, x greater than 0 is an open interval. It's an infinite open interval. Both of them have the same derivative. So f prime is 1 over 7x times 7. That's 1 over x by the chain rule. G prime of x is also 1 over x. These two functions are not at all the same function. They do have the same derivative. How can that happen? Well, it's because if you use the identities for natural log, you see f of x is really a constant plus g of x. In this case, the constant is natural log 7. Here's another example. Take inverse sine and negative inverse cosine. Both of these functions have the same derivative, 1 over square root of 1 minus x squared. These are defined on the open interval from -1 to 1. So what's the explanation in this case? Sine and cosine, or their inverses for that matter, are not really the same thing. But what it means is that f and g have to differ by a constant. That says inverse sine plus inverse cosine would have to be a constant. What would that constant possibly be? Well, if it's constant, you can take any point in the interval, say it's 0, and you'll get f of 0 minus g of 0. That's 0 plus pi over 2 is pi over 2. So that must be the constant, because you get that value at a point of the interval, and everywhere else it has to be constant. So it's pi over 2. Now that's not the only way to see this identity. You can also do it by looking at a right-angled triangle, and the fact that the two acute angles add up to pi over 2 is also giving you this identity. But it's a good way to use derivatives to come up with an identity in this case. We talked about using derivatives to test for a function to be constant. Now let's use derivatives to check when a function is increasing. But I better tell you what increasing means first of all. It's not really a calculus notion, it's a pre-calculus notion. A function is increasing if its graph rises. That is, every time you move to the right on the graph, you go up. A function is increasing if its graph goes up every time you move to the right. What that means is if you take 2 points in the domain, A and B, f of b is bigger than f of a. If b is bigger than a, then f of b is bigger than f of a. So the theorem says that you can test at least for a differentiable function when it's increasing. If the derivative is positive, then the function is increasing, and conversely. To prove this, again, it's a very short proof. Suppose that the derivative is positive, and you look at 2 points, a less than b, in the interval. According to the mean value theorem, there's a point in between, a point C, where the derivative is the average rate of change over the interval AB. So if f prime is positive, then your average rate of change on that small interval AB is also positive, and that means that f of a is less than f of b, and conversely. So if f of a is less than f of b, the average rate of change is positive, the instantaneous rate of change is therefore positive, the derivative is positive. Now it's tempting to look at this theorem and say, well, you don't need a theorem to tell me that. Increasing means derivative is positive, it's going up. But the derivative is about instantaneous rate of change, whereas increasing is about average rate of change over a larger interval. And why should they be the same thing? It's only because of the mean value theorem you can make that connection. Everything we did for increasing functions, you can also talk about for decreasing functions. A function is decreasing if its graph goes downwards. You don't need a function to be differentiable or even continuous to talk about this. This is a pre-calculus notion. It just means that as you go to the right on the graph, it goes down. Move to the right, it goes down. So if A is less than b, then f of a is bigger than f of b. Just like before, if you have a differentiable function on an open interval, if the derivative is negative, the function is decreasing, and the other way around. If the function is decreasing, the derivative is negative. I want to round out this video with some examples of functions just to clarify what is meant by increasing and decreasing. Here's a function on an interval 2, 8. It's not continuous, not differentiable at 7. It's not continuous at 4. That doesn't matter. I can certainly talk about increasing and decreasing. Well, this function is increasing on the interval 2, 5, and it's also decreasing on the interval 5, 8. But on the entire domain, on the domain from 2 to 8, it is neither increasing nor decreasing. Most functions are not increasing or decreasing on their entire domain. It very often happens that on certain intervals, it's increasing or decreasing. And by the way, at least in our course, when you get to talking about intervals where a function is increasing or decreasing, don't worry too much about the endpoints. We're not going to fuss over that in most of the examples and when it comes to grading. So I could just replace all these closed intervals by open intervals, and what I'm saying would still hold true. So open or closed interval here, everything I've just said is true. You have a function that is, overall, it's neither increasing nor decreasing. But on some certain intervals, it could be increasing or decreasing. Now here's a function that is defined on the interval from 1 to 7. It's increasing on the first part, on the interval 1 to 4. It's also increasing on the interval from 4 to 7, but it is not increasing or decreasing on the entire domain. It's neither increasing nor decreasing. So to be increasing on part of the domain and increasing on another part of the domain doesn't mean it's increasing on what you get when you put those two parts together. It doesn't. If you go back and look at the definition, you'll see why. Because on this graph, if you take a point in the left half and go to the right, you could end up going downward. So that's not increasing. And if you look at the graph and say, but whoa, it's rising, it's got a tangent line that goes upward. Well, whoa. Tangent line is about a local property. That's not about a global property, which is what increasing refers to.